Hi everybody, thanks and welcome to this meetup. My name is Laurence Moroney. I work at Google. I've been working at Google for about 5 years. I've worked on various things from cloud to Firebase, and then just recently in the last 6 months or so, been working on TensorFlow. I do a lot of work as my role's called a developer advocate, so I do a lot of work particularly scaling, talking about our message. So if you've seen the youtube.com/TensorFlow channel, I'm all over that because I run it. And if you haven't, please subscribe. We need all the subscribers we can get. And so just quick story actually that, I studied in the UK. Do I sound American to you? I do, okay. I'm not actually American, well, I'm naturalized American now, but I grew up actually between Ireland and Wales. And I studied in the UK and I graduated in the UK in 1991, right into the middle of a really, really horrible recession. I don't know if anybody remembers that. Many of you are probably too young. But back then, like when I was really young and I was trying to find some work, I actually was working as a temp for London Underground, just not far from here. It was my first job out of school. But then I got laid off on Christmas Eve. Lovely. So while I was looking for a job, there was only 2 newspapers. I could only afford to buy a newspaper twice a week. And one of those newspapers was the Telegraph. And so I was a big fan of the Telegraph newspaper, so it's actually it was a great privilege to be here. But I only bought the Telegraph 1 day a week, and it was on a Wednesday. And anybody think back to 1991, it was a massive innovation that the Telegraph had that I'm sure their sales spiked on Wednesdays. And does anybody know what it is? I'm looking at the guys from the Telegraph and they're going, oh crap. And it was it's amazing that it was a very low technology but high innovation. It was something that the Telegraph did and the Telegraph led in, and that was fantasy football. And so I think you guys were the ones who introduced that to the UK. And this is nowadays, if anybody play fantasy sports, fantasy football? Okay, a few, cool. And so it was a great way of increasing how I interact with one of my favorite sports. Right? It used to be if I wanted to watch football, I'd watch Match of the Day on a Saturday night. And I'm a big fan of Liverpool. Oh, cheers. Thank goodness. I thought there'd be booze. But when I lived in London, obviously I also got to like Arsenal as well because I live pretty close to them. And it was okay, I'd watch Match of the Day and I'd watch Liverpool and I'd watch Arsenal, and then the rest was kind of boring. But then fantasy football kind of increased my engagement with the sport because you'd pick players and I might have a player from Middlesbrough or Watford or something like that. And then I'm cheering when they score, even if they're playing against my team. And those kind of innovations increased my engagement with this game. But back then, it was you didn't have the internet and you didn't have stats being updated right away. And your source of truth for stats was it was a table that was printed on a Wednesday afternoon in the Daily Telegraph, or in the Wednesday edition of the Daily Telegraph. So then you'd in your office playing with all your friends, that kind of stuff, you'd take a look and it was this player scored this player scored this, and you'd huddle around and it was amazing. And it was very low technology, but very high innovation. So it's something, the Telegraph to me have always been there as a very highly innovative newspaper. So thank you for that. And thanks for inviting me to speak tonight. But let's not talk about the past anymore. Let's talk about the future. And talking about the future, and one of the things that I work on at Google is artificial intelligence and machine learning and TensorFlow and deep learning and all these kind of concepts that you've probably heard before. But when you think about artificial intelligence and when you see artificial intelligence portrayed in the media, you tend to see things like this. Okay, so it's there's a small search engine called Google that I did a little search for AI on. Anybody heard of it? And this was something that showed up on page 1 when I was searching for it. And it was titles like robots will destroy our jobs and things and this was actually the Telegraph, by the way, but it was back in 2016 to be fair. And it was robots will take over most jobs within 30 years and rise of the machine, the future has lots of robots. And the way search engines tend to work is that one of the things they work through is association. And you can see the word artificial intelligence got associated with robots. And then it got associated with jobs. And then it got associated with fear. And it's all these kind of things. And I took on this job to work at Google on TensorFlow because I think as an industry, we've done a really bad job of explaining what artificial intelligence is and the opportunities that are available for you in artificial intelligence. And as a result, this is the kind of thing that we see. And it doesn't stop there. Okay, I love Elon Musk and I love what he's doing with Tesla and the Boring Company and all these kind of things, but he's very open about talking about how it's humanity's biggest threat. I personally think biological ignorance is a much bigger threat, but don't quote me on that. And then there was a marketing company that they decided to do a little bit of a parody on this by seeing that how people talk about artificial intelligence, that they did a search and replace on a number of titles, and they did a search and replace of artificial intelligence, and they replaced it with demonic possession. And then you end up with titles like demonic possession helps advertisers be more compassionate. And it's amazing how it kind of makes sense. And I think my personal favorite is demonic possession now fits inside a USB stick, which tells you a lot about how we've been talking about artificial intelligence when demonic possession, fits perfectly in the search and replace. And then, the biggest threat to artificial intelligence, human stupidity. To be honest, the biggest threat to us all is human stupidity. But, these are some of the kind of things that, the industry has been saying. And here again, it's like, and this was like a bunch of newspapers in the UK, including the Telegraph and the Guardian and others, that I wanted to take a look at what they're saying. And these were some of the titles that, one thing that I have to say about this country, and it's often very easy when you live in a country to think that this country does a really bad job of things. But I have to say, this country, the UK, you're doing a great job with getting people ready for artificial intelligence. And just look at some of the things that I found in some newspapers. Things like, CIOs must put AI on the fast track. Companies want to implement more AI but struggle. We're trying to help with that. Artificial intelligence will impact artificial intelligence and the coming health revolution. And actually, my personal story with artificial intelligence began right here in the UK. Almost 30 years ago. And I mentioned that I could afford 2 newspapers a week back when I was unemployed, when I was living here. The first was the Telegraph on the Wednesday, because of fantasy football. The second was the Guardian on a Thursday. And I don't know if it's still the same, but back then it used to be the Guardian on a Thursday had a whole section dedicated towards tech jobs. So anybody who was unemployed and anybody who was in tech, you'd buy the Guardian on a Thursday and apply for these tech jobs. And back in 1992, the UK government actually started this amazing initiative. And who remembers the Prime Minister at the time? John Major, thank you. So John Major was the Prime Minister at the time. And I try not to talk about politics, so forgive me if I'm just going to mention politics for a little bit, because sometimes people, they don't like one party or they don't like the other party. But what he did at this time was something that was so forward-looking and so driven by headlines, not like that one, so driven by headlines at this, that he actually started a program to train a lot of British developers in artificial intelligence in 1992. Okay? It's kind of unheard of when you think about it. And this program got advertised in The Guardian, and he did a talk to the House of Commons, and he was talking about how artificial intelligence is a wave of the future, and we need to train developers in it. And the government funded a program to train 20 developers, and you had to be unemployed, and you were unemployed for 6 months, and with like a degree and all these kind of things. So I applied for the program through The Guardian, and I was actually the first person accepted into it. Unfortunately, the hype cycle being what it was at that time for AI, that the program crashed within 6 weeks, but at least it was beautiful forward vision from the government, and that gave me a platform to move into other things and help me to be where I am today. So rest assured, you're living and working in one of the best countries, I believe, for having forward vision for people who live in that country. And artificial intelligence is one of the waves of the future. But what is it? I've spoken a little bit about what it isn't, and I've shown funny headlines about what it isn't and all these kind of things. But what actually is artificial intelligence, and what is it for developers? So here's how I like to think about it. So in classical programming, you have rules and data that go in, and you have answers that come out. You want to write a program, your code that you write is the rules. If this, then that. While this, do that. All of these kind of things. Those rules are then driven off of data. You compile that into something, and then that something gives you the answers that you need. So machine learning is what I'm going to be focusing on tonight, and it's one of the pillars of artificial intelligence. All machine learning does is a bit of a remix of this. And what machine learning is answers go in, data goes in, and the rules come out. The rules get inferred from this. So think about this as a developer. So there are many programs that you can write, and there are many apps that you can write that are perfectly fine with if this, then that, while this, do that. But think about those scenarios that doesn't work very well for. Right now I'm wearing an Apple Watch. Anybody else have one? Okay, quite a few of you. Anybody do the fitness stuff on Apple Watch? Okay. Now think about the logic that has to go into this for determining, am I running? Am I biking? Am I walking? Am I on a treadmill? Am I playing racquetball? Now think about that if you were doing a lot of if-then rules. Okay, I'm a very slow runner, and I run with a friend of mine who's a very fast runner. And when she runs, I mean, she's probably as fast running as I would be on a bike. But when I'm running with her, is it detecting that she's walking or is it detecting that she's running because she's slowing down to my pace? You know, or if I try to keep up with her, I'm probably going as fast as I would normally be on a bike. Now am I biking or am I running? And it gets it right every time. It's really, really cool. And this is all driven off of machine learning. And it's driven off of machine learning because they feed in answers and they feed in data. Okay, so the answers are, they've trained this on millions of hours of people exercising. I don't know if you saw WWDC a couple of weeks ago. One of the new things in Apple Watch is even swimming, right? So they've trained it on, they have thousands of people running for thousands of hours. They have thousands of people biking for thousands of hours. So the answers are saying this person's running. The answers are saying this person's biking. The answers are saying this person's swimming. And then there's all the telemetry that comes from the watch. And all of those then get fed into machine learning, and then the rules get inferred out of that. So instead of you having to write the rules yourself, if this, then that, then the machine learning engine has actually built that for you into something called a model. So the model that exists on this is a really good model for detecting whatever activity I'm doing right now. And there are tons of scenarios that, you know, you probably see demos, and I'm going to show one later, for example, of things like image recognition. Now think about, like, if you were to write rules for image recognition, this is a dog and this is a cat. You know, it's like, what kind of rules would you write for that? You know, if it loves you forever, no matter what you do, it's probably a dog. And if it's currently plotting your murder, it's probably a cat. But those are kind of hard to write code for. And so then, like, if you think about image recognition, maybe you think pointy ears means it's a cat, but some breeds of dog have pointy ears, that kind of thing. And so as a result, whole new scenarios are being opened up for you as a developer when you start thinking in these terms. Now, typically when you start thinking of machine learning and you start seeing machine learning, there's two broad things that you'll go into. One is classification and one is prediction. And you might think that's actually really narrow. You know, maybe as I'm a developer in financial services, I don't need to do prediction, I don't need to do classification. But when you start thinking a little bit deeper into this, almost every problem that you can solve can be solved by either prediction or classification. You know, in financial services, analysts usually have a rating, right? Buy, strong buy, hold, all of those kind of things. They do that based on rules. You know, hey, if the stock is above its 200-day moving average, maybe I should change. Or if the recent filing that they did, that they made more money than before, I should change. These are all if-thens. And there's limited number of scenarios that you can program in an if-then. But when you start feeding off of answers and data to infer these rules, you've just opened up a whole new bunch of possibilities. So here's the two of them side by side. Rules and data in, answers out is your classical programming. Answers and data in, rules out is your machine learned programming. And I want to give an example of, so to go back just to this for a second, answers and data in for machine learning, an easy way to show this is with a game. And the simplest game I could think of was noughts and crosses. It's called something different in every country. It's like tic-tac-toe in the US, it's noughts and crosses here. I gave this speech in Japan a couple of weeks ago, and there was a weird name for the game that I can't remember. But if you think about noughts and crosses, right, it's an easy one for you to compare both of these in. Now, if I'm going to write a traditional game for noughts and crosses, it's really easy for me to write the rules that can tie or beat a human. Okay? I mean, what's the first rule that you would do if you're writing noughts and crosses and you want to win the game? And say the computer's moving first. What would you do? Go in the center, right? You know, you don't have any hope of winning if you don't go in the center first. And, or for example, then if you're going second and the human's gone in the center, what do? You have to go in a corner, right? So if you've ever played a game and somebody goes in the center and you don't go in a corner, you're almost always going to lose. So if I'm writing code to do this, it's actually very easy. But if I want a computer to learn how to play noughts and crosses, I don't tell it the rules. It's like if I'm playing with a 3-year-old. I draw the grid, I get to play, and I go, ha-ha, I beat you. You know, and then I'll do it again, ha-ha, I beat you. And I'll do it again, ha-ha, I beat you. And he'll do it a number of times until the kid will usually figure out, I got to go in the middle first. And then it takes a little bit longer for them to figure out, you know, if you've gone in the middle, I got to go in a corner. So I applied this as a machine learning problem, and I want to show a little video of, this was me playing against it on an Android device. So I decided to do this so that the computer was completely naive. The computer's going to go second. There's no rules at all. I started playing with my own rule that I'm going to go first in the center, so I'm X. And then my second move will be, I'm going to go to the one immediately to the right of the center. And so the computer, being completely naive, just goes, every time it's going to go in the first available spot. But if it loses, it will remember where it lost and then try something different the next time. So I'm just going to run that video, and we should see it. Okay, I go in the center, I go to the right, I go up there, I go to the bottom, I win. Okay, so we try it again, and it goes, aha, it already determined that the best place for it to go was the bottom right-hand corner, but I still won. So then it's trying something else, I still win as its third move. If you look at the third move the computer makes, I still win. Again, look at the third move the computer makes. It hasn't figured it out yet, I still win. Now when we look at the third move the computer makes, this time I won because of the second move the computer made. I went to the top right. It actually beat me this time. You know, it starts actually, I'm dumb, and it even beat me at noughts and crosses after a few turns. But this was a case of there were no rules defined. The only thing was that whenever the computer lost, it would remember what it had done when it had lost, and it fed that into a machine learning algorithm. So then in future it would say, I'm not going to do that again. I'm going to try something different. And then after a while, only just a few games, like 10, 15 games, it ended up tying me almost every time, or drawing with me almost every time. So that video is on YouTube. I can share it with you all later. Let's move on to the next slide. Okay. So now let's think about machine learning. It's something a little bit more interesting than noughts and crosses. And one of the things I've been working on is actually breast cancer detection. So thinking about breast cancer detection, I mean, if I was just using rules for this, it would be really easy if the data was that easy. So for example, if green cells are benign and the red cells here are malignant, it's pretty easy for me to write a rule that looks something like this. Right? And then I say, hey, if x is greater than 30, then it's malignant, where x is the radius of the cell. And if it's less than 30, then it's going to be benign. You know, that'd be easy, right? But unfortunately, our data is never that easy. Maybe our data is going to have multiple dimensions, and it looks something like this. So now, you know, what would my decision boundary be here? So by decision boundary, I mean this straight line that says, hey, if it's above this, it's benign. If it's above this, it's malignant. If it's below this, it's benign. We call that a decision boundary. And like now I'm taking a look at two different axes of my cells instead of one, and go, okay, you could pretty simply draw a diagonal line down through here and say, you know, here's my decision boundary, and anything above and to the right of the line is probably malignant, and anything below and to the left of the line is probably benign. But again, you know, this is a little bit oversimplistic, and you know, the real breast cancer data set will look something like this. Okay, so now, so this was a set of public domain data from Wisconsin University, where they took about, I think it was about 800 different biopsies. And based on the biopsies, and they reported on, like, you know, a number of about 30 different features of a cell in the biopsy. And based on those 30 different features, and when I say feature, that's just like a data point, like radius or size and those kind of things. And so some were malignant and some were benign. How would I draw a decision boundary for this? You know, I could do something like that. It would be kind of naive, right? And you don't want to, for something as dangerous as breast cancer, you don't want a bad diagnosis because you have a naive decision boundary, right? You don't want to tell somebody that you're all clear, it's benign, when it's actually malignant. And if you see, there's quite a few red cells to the left of that line. You know, so it's like, well, how do you start doing these kind of things with if-then rules? And so like I zoomed in on one of the areas, like here you can see it's very clustered right there. So I zoomed in on one of these, and even then it's not as simple as you think. There's a lot of red on the left, and there's just no way for me to easily come up with like an if-then set of rules that's going to work for this data. And I might have hundreds of these that will actually end up working somehow, but then I bring in a whole new set of data and it could throw them askew. So what do? Well, this is basically how machine learning works. So I'm going to go back to the simple example here of this line. And then I know that everything above the line is malignant and everything below the line is benign. And I always mix up those two words. So how this works in a machine learning type of programming is you think about developing something called a neural network. And it's one of the things that we've done a really bad job of communicating this, that when people see neural network, they instantly think it's an emulation of the human brain. It's not really. It's just basically a set of mathematical operations that you use. And they run some kind of feedback, which I'll talk about in a moment, so that you can, and it kind of runs like a network with one layer feeding into another, but it's got nothing to do with neurons in your brain. It's a very, very rough approximation. And I think when people saying, oh, Google are programming neural networks, you know, that they're building a human brain, that's not really true. You know, a neural network is something completely different. And like a very simple one will look like this. And then I'll go like, okay, if you remember that decision boundary that I was talking about earlier on, I have a bunch of radii, where 18 is benign, 17 is benign, 13 is benign, and then 31, 35, and 39 are malignant. Instead of writing the if-then code in neural network speak, it'll be a case of I'm going to run an operation on that in my layer. And the one operation is called ReLU. It's a very common one. And it's just a mathematical operation that's the equivalent of saying, if the value is less than 0, make it 0. If it's greater than 0, keep it as itself. So you get like a little line like this one. So I say, okay, I'm going to run an operation ReLU of radius minus 30, and that's going to give me either 0 or something. And then I'll say, if it's something, now I know it's malignant. If it's 0, I know it's benign. And very simple, right? So this is like the building block for what a neural network will look like. But let's make it a little bit more complex. Now let's think about this one, and we'll see where machine learning comes into it. So now I have this chart and I have this line, and everybody remember from school the formula of a line, right? Y equals mx plus c, okay? So now I have like y equals mx plus c will define this line. But what is y? Well, I want to know y, but what is m and what is c in this case? And if I can figure out what m is and what c is in this case, then I have a formula for that line, and I can figure out what's above the line and what's below the line. So in neural network speak, that would be something like this. I'm going to have one layer that's figuring out the m, and I'm going to have one layer that's figuring out the c. And out of this, now that I know my m and I know my c, my output can be y equals mx plus c. And I have actually a formula, and I have a model that will define what y equals mx plus c is. So I'll throw a bunch of data at that. But typically one of the things, and we'll be hearing later about data science, and as part of data science is like figuring out your data, figuring out the right way to formulate your data, and all that kind of stuff. But one thing that you'll do is when you've got a big data set, you're going to hold back a piece of that you're going to use for testing. So take for example, you're going to get 20% of your data that you put aside, and then you train the model on 80% of your data. And then if your model says, okay, I figured out what m is, and I figured out what c is, then you can take your test data and say, okay, I know the answer in my test data. I'm going to try out the m and the c that you've given me, and let's see if it works or not. So that's something that you'll typically do. Hold back this test data, and then you can evaluate your neural network based on that test data. And then the process for that is going to look a little bit like this. So we're going to start off by guessing the line. Okay, I'm going to guess the line is here. And a little bit like my tic-tac-toe, or noughts and crosses, that when I first started playing tic-tac-toe, the computer got it wrong because it guessed the right move. And it took a little bit of time and a little bit of experience before it started getting it right. So this is a really naive line that I'm guessing. But this line has an m and it has a c. Right? I'm going to say in this case, well, if m is 0 and c is 5, y equals mx plus c gives me that line. So now I go and I start trying to train. Okay? So I'm going to feed in an x, I'm going to feed in my m, I'm going to feed in my c, I'm going to try it for all my data, I'm going to test which ones are right and which ones are wrong. And if you think about this line, how many of them are going to be right and how many of them are going to be wrong? But the green B's below the line are going to be right, but everything else is going to be wrong. So my error rate is going to be really, really high. So what I do is I take my test data. There's a function called a loss optimizer. I'm not going to go into all the details of loss optimization. When you start learning machine learning, there are things like gradient descent and stuff like that, which are all just ways of trying to figure out where you went wrong so that you can re-optimize to try and get it right. But I'll feed that into my loss optimizer. My loss optimizer will push back and say, okay, try this M, try this C. And then it will go through a number of iterations of that, continually refining M and C until it gets it right. And the process might look a little bit like this. So now it goes, okay, that was horribly naive. That was completely wrong. Let's try these values. And now it's like, hey, it's not bad. We're getting quite a few right, but we're also getting quite a few wrong. Okay, and this is something you don't want to get wrong. You don't want those malignant cells to be diagnosed as like, nah, you're fine. So we go, okay, we're just going to try, hey, if M is 0 and C is 12, we'll do this, but we're having an unacceptable error rate. So what do? Well, let's try something else and try something else and try something else until we end up with something like this. And we say, hey, if M is -1 and C is 20, now with all of my data, I'm actually getting 100% right. So when you start seeing reports about machine learning, anybody see the one in the news yesterday where it's saying like Google can guess with 95% accuracy when you're going to die? I don't want to read that. And, but what they're really talking about, and sometimes there's an old saying, there are lies, there are damned lies, and there are statistics. This seems to be one of those. More it's a case of they have a model, or Google have a model, where they fed in a bunch of data about life expectancy, and then they verified that against a test set, and it was 95% correct. That doesn't mean that the 95% able to predict when you're going to die. That means, based on the data that we used, that 95% of those were correct. There's a slight difference in axes there. And this is this is how machine learning, and this is really the core of machine learning and how it all works. But you know what? We're developers, we're not mathematicians. So we'll talk about code in a second. But let's go back to this. We don't have a straight line, right? We're going to end up, we don't have a straight line for this. We're going to end up with like some kind of weird curve like this. And even then, this weird curve isn't that right. And if you look closely, actually, this data I'm plotting is 3 different dimensions. But remember when I said with this data, there's actually 30 dimensions. I'm plotting 3. There's X and Y axis, but consider an implicit Z axis from the size of the dot. You'll see the green ones on the lower left are small, and the red ones on the upper right are large. So think about like you're trying to view down this in 3 dimensions and maybe draw a plane, which is your decision boundary there across all of these. But when there are 30 features, you might have 30 dimensions, and your formula for 5 dimensions would look like this, right? M1 times x to the 5th plus M2 times x to the 4 plus M3 times x to the 3, et cetera, et cetera. So how do you infer all of those to be able to draw that curve? It's basically the same thing. You just have lots of layers. And each layer has a job of determining the weight and getting an output. You pass test data in, you've got a loss optimizer, and then that loss optimizer, every iteration will help you rebalance those weights so you can figure out what M1 is, what M2 is, what M3 is, all the way down to C. And the good news is when you're using a framework like TensorFlow, you don't write these loss optimizers yourself. There's a bunch of standard ones, stochastic gradient descent, atom, and stuff like that, that are just built into the framework for you. I'm not a mathematician, I'm a programmer. Thank God that I don't have to write those for myself. I would just use those loss optimizers. And then that would give me something like, a curve like this. In this case, the diagram is wrong because there's still a lot of, benign ones above the line, but at least there's the number of misdiagnoses where you're saying something is benign, where in fact it's malignant, have been greatly reduced. And then, again, this is just a visual. But just to give an example of training a neural network on this data using a framework called Keras, and I blogged about it, it'll be on my blog, I got it to about 98% accuracy of determining a malignant cell. And so that doesn't mean that it's 100% accurate, of course, but, using a relatively small set of data, about 600, it was able to train it to about 98, almost 99% accuracy. Now, I don't advocate that this should replace a doctor, but I think this should be a tool that a doctor could use. So, for example, if, a doctor takes a look at a biopsy and from the biopsy is able to figure out that this cell is absolutely benign, then that's good news. Or if the thing figures out that it's absolutely malignant, the chances of it being malignant are very high, then they can go for further tests. And they can, using a tool like this, I find will allow a doctor to test more people in a shorter space of time. With a shortage of doctors around the world, I think that's a good thing. So the process then will end up looking a little bit like this. So for example, you take a biopsy. It's called a punch biopsy, where they pull out a little piece of flesh. And then from that biopsy, you do what's called feature extraction. And this is going to be the same in any machine learning thing. Feature extraction is one of the keys. So they scan the cells and they pull out features from that. They look at the nucleus, they look at the shape of the cell, the size of the cell, those kind of things. Then that data, that feature extraction, is then fed into a neural network. The neural network at the end is going to have an output layer. Right now, I'm just classifying for 2 different things, a malignant or benign cell. So you see there's just 2 output layers at the top. That's going to give me my estimation. That's going to give me my prediction, that type of thing. And I actually wrote this in about 60 lines of Python. So this, just tell you how simple some of this stuff is beginning to get. And then with TensorFlow, when you're using it, there's a thing called TensorBoard, which allows you to then kind of look inside that neural network to see what that neural network's doing and help you debug it, help you to figure it all out. So I'm just showing a little video of that. So that's, the core of, I said at the beginning, we do a very bad job of communicating what AI is. So that's machine learning and deep learning fit into artificial intelligence as a bigger picture. Deep learning is really when you start, it's a subset of machine learning, and it's when you start using large neural networks with multiple layers to do a lot of extraction and to find patterns that, even a shallow learned thing, a typical machine learned thing couldn't find. You know, those are really part of the same thing, and those are part of the path towards artificial intelligence. So if you think about, say you wanted to build a robot, and then you wanted that robot, for example, to be able to recognize things. You know, you want a robot to see a cat and know that it's a cat. You want a robot to see a dog and know that it's a dog. Instead of you coding all of those if-then rules, that's the idea where machine learning can come into it. Similar that you have with one of these things where I sometimes see I'm turning myself into the robot. You know, that's really what it's all about. So think about, you know, machine learning is a programming paradigm that you can do and you can do today, and is part of the path towards artificial intelligence. But that's all it is. It is just that simple programming paradigm. It's not a threat. So TensorFlow, as I mentioned, is a toolkit. It's an open source toolkit. It's a machine learning platform for everybody that we've built for solving problems. So think about the programming problems that you can't solve today because they're too expensive or too infeasible with traditional programming, and you might be able to solve them using machine learning. I give one example. I was going to roll a video, but there were some sound issues. But we actually worked with a group in Tanzania. And if you go onto YouTube, you'll find the video. And farmers in Tanzania relied heavily on a crop called cassava. And the cassava root is really fascinating in that it provides a lot of nutrition and provides it very cheaply. But when one cassava plant gets diseased, an entire field, an entire crop can be lost. And the problem is that you can't tell the disease by eyeballs until it's too late. Okay, once you've spotted the disease, that plant is gone. All of the plants around it are already infected, even though you can't see it yet. Travels like the common cold, and it can be disastrous if a cassava crop fails. So with Carnegie Mellon University in Pittsburgh and a group in Tanzania, we actually built a neural network using something called TensorFlow Lite that I'll talk about in a moment, that you can run on a phone. And the neat thing about this is it doesn't require any connectivity to the cloud, because in Tanzania they don't have 4G, 5G cell connections, that kind of thing. And you can run it on an old phone, and what they do is they can scan the leaf with their phone, take a picture of it, and it's been determined that these things can spot the cassava disease in the leaf long before a human eyeball can, and as a result they can find the diseased plants before the disease actually spreads. And so they can rip out those plants and, as a result, save crops. You know, it's begun rolling out in Tanzania this year, and it's going to be rolling out in other African countries, or any other, starting in African countries, but it's designed for the cassava leaf, which primarily is grown in Africa. Some countries in South America, I believe, also grow it. But it's been designed with that in mind, and it's like, if you were to write if-then rules for this kind of thing, you wouldn't be able to do it. You know, this kind of thing has only been made possible using scanning images of these things, extracting features from that, training neural networks, and then somebody in Carnegie Mellon University took thousands of healthy leaves and thousands of diseased leaves, extracted the features from them, trained a neural network on that, and found out that it was like 99.9% accurate. So now they can roll this out in the field. It's really, really cool stuff. So it's been designed, TensorFlow, it's been designed to run with many languages. We've recently just announced Swift and JavaScript. I'll talk a little bit about JavaScript later. I haven't really worked with Swift. And so again, as a programmer, it's really a toolkit for you. And I like to talk about TensorFlow to programmers. So thinking about how do you start doing this? How do you start building these things? How do you start building these models? I'm not a mathematician. You know, I did the breast cancer stuff just by knowing a little bit of Python. You know, I don't know anything about breast cancer. I'm not a doctor or anything like that. I just started getting the data, feeding it into a network, running a test against it, finding it was 80% accurate, tweaking it, running another test, finding it was 95% accurate, and continuing to tweak. So as a programmer, there's really these 4 steps. Number 1 is you got to gather your data. Okay, so you gather your data, you read it from a data source, and you put it into a format that works well with your programming language. Almost everybody has data nowadays in CSV format, which is ancient. But as a result, universities, it's a very reliable data format. When I've worked with universities, they put everything in CSV. They might have it in a SQL Server database, but they'll read it out, query it, and format in CSV, that kind of stuff. You know, think about your data source and think about how you would ingest that into a programming language. It might be CSV, or you might be really cool and able to read the stuff into Python or JavaScript yourself directly, you know, reading it as JSON or stuff like that. But that's your first step. Got to get your data, got to gather your data, and got to have it in a format that works with your programming language. Then the next part, which is really the core of data science, is to process your data. Okay, you got to choose the features and the labels. When I say features, that's the X's. When I say labels, that's the Y's. So if you think about my lines earlier on. So when we look at, for example, breast cancer detection, the labels are very easy. Either this cell is malignant or this cell is benign. Then when we start thinking about our features, we'll think about all of that data that was associated with breast cancer cells, like I was saying, the size of the cell, the shape of the cell, the nucleus, that kind of thing, the color of the cell, those kind of things. So you choose those features and labels that are going to work for you. And then you got a little bit of programming, and it's a little bit different than you might be used to as a developer, is you got to formulate your data to optimize it for machine learning. And I'll give one great example of this that is very unintuitive to developers, but it's something that we call one-hot encoding. Has anybody heard of it? Okay, one or two. So I'll talk about it this way. So take, for example, I'm building something that will recognize 5,000 different images. Okay, from bananas to apples to dogs to cats, all those kind of thing. Now you might want to say, okay, I'm going to just create an ID for each of these. If it's ID 0, it's a cat. If it's ID 1, it's a dog. If it's ID 2, it's a banana. Those kind of things. So now I just have that one piece of data, which is going to be an integer. It doesn't store very much. And that's probably my most optimum way of storing if something is going to be a dog or a cat or banana or something like that, right? That's how we programmers do it. Machine learning, you go crazy. So what you do with machine learning, say there's 5,000 different things that you want to classify, you create an array of 5,000 integers. And you would set that array to be 0 at the index for everything except the one that you want, where you'd set it to be a 1. So for example, remember earlier on I was saying like a banana is 0, your array would be 5,000 integers long with banana being 1 and everything else being 0. And that's called one-hot encoding. So to me as a developer, I was like, this is dumb. Why on earth would I do this? Because it's not optimal. I'm taking up tons of memory that I really wouldn't want to take up. And the reason for it is, if I go back to this chart from earlier, remember earlier I was saying that you want to train it with something, you want to train it with data. So for example, in my breast cancer, there's two types of data. There's malignant and there's benign data. So you want to train it so that here's what a malignant cell looks like, here's what a benign cell looks like. And at the end of my neural network, my output layer, I'm going to have the same number of cells as the classes I want to identify. That's the most efficient way of doing it. So then what I want to do is, like in this case, for example, if I have a benign estimation that I want the output layer, the cell on the left to give me a 0 and the cell on the right to give me a 1. And that way I'll know, the node on the left to be a 0 and the node on the right to be a 1. So that way I'll know when I look at this one that this neuron is firing, this neuron is active, and as a result my estimation is a benign. So when you think about that, if I'm classifying 5,000 different things, I would do exactly the same way. So when I train it, remember it's just a really dumb piece of math, but I'm going to say, here's an array of 5,000 things, and when you see a banana, I want you to give me back the same array. As in, I want that node to be active and the other 4,999 not to be active. So that's what one-hot encoding is all about. It's you shape your data going in the way you want the data to come out, the way you want those neurons to fire on the way out. As a programmer, it took me quite a while to get my head around this because I thought, it's just really dumb for me to take, one integer and turn it into an array of 5,000 things. But that's what we call one-hot encoding, and it ends up being amazingly useful to make it much easier for you to train your network. Instead of having your network try and come up with a value between 1 and 5,000, you've got 5,000 nodes. One of them will say it's me, and the other 4,000 will say it's not me. And so that's when I start talking about processing your data, is formulating it to optimize for machine learning. We've all been programmers. I've been a programmer for many years. We all have it in our heads that it's all about optimizing, making things smaller, making things more efficient. And here's a little bit where you have to change how you think. So then the next part is to train your model. So experiment in designing your network. I glossed over it a little bit earlier, but like every time you have a layer in your network, you have something called an activation function, and you've got something called a loss optimizer. And the idea behind this one is that an activation function is just a way of applying math to something to do a lot of if-thens for you. So let me give an example. I showed the ReLU earlier. Remember that one? Say, hey, if it's greater than 0, keep it. If it's less than 0, throw it away. So in machine learning, you would, instead of you having every piece of data you having to execute that if-then on, you just say, I'm going to say ReLU is my function on this, and then the TensorFlow, the tensors in the engine will apply all that math for you, effectively doing all those if-thens. Another one is something called a sigmoid function that you'll see a lot. And all that is that, say you've got a range of values that you want to put between 0 and 1, instead of you, for every value, having to do an if-then on that one, there's something called a sigmoid function that will actually automatically map that for you based on the range. So a lot of times when you start reading some of the literature and you start reading some of the tutorials, it starts getting into the math really quickly. You start seeing sigmas and you start seeing summations and all that kind of stuff. My advice to you is don't worry about that. The nice thing about it is when you understand what some of these functions are supposed to do, you just pick your function and you apply it and let TensorFlow do all the math for you, or whatever machine learning framework you're using to do all the math for you. The idea is to take all those if-thens out of your hand and map them into math functions. So that's when I talk about experiment and design your network and optimize it for accuracy. Optimizing for accuracy, again, ends up you do things like one-hot encoding. You know, as a programmer, I'm used to optimizing for size, but when you're training the model, it's really all about optimizing for accuracy. And then finally is to use the model. You know, as a programmer, you write code, you compile it, you get a binary blob. That binary blob is what people use. With machine learning, it's very similar. You know, you create this model, and then this model you can then use in something, and this model will run what we call inference for you. It's still just a binary blob. But you're going to have to wrap it in something, maybe a serving environment where, you know, people type stuff in a web server, and it'll give you back the prediction or the classification of that. Or maybe on mobile, like I mentioned with the cassava leaf. And then improve and update as new data becomes available. So one of the neat things about this is that, you know, if you write your application wraps a model, then you can, as you get new data and you get better accuracy in your model, all you got to do is ship a new model. It's like shipping a new JPEG to update, you know, a mobile application, something along those lines. Just ship a new version of that binary blob, keep your application the same, and the application's behavior can improve. So mobile, and let's talk about mobile, one of the things I'm most passionate about. So I've mentioned machine learning, and I've mentioned building models. So with TensorFlow, you do all of these kind of things. You get this binary blob out of it called a model. Now this model can be big. This model isn't usually optimized for a small device like a mobile. It's optimized for powerful machines with GPUs, all that kind of thing. But with TensorFlow Lite, we've decided to try and take this to mobile devices. And at TensorFlow Lite, it's a set of tools. The first of them is a converter, where the idea is that this model might be big, it may be optimized for heavy machines, like I've said. So what the converter does is that does something that we call flattening the model. A lot of variables get converted into constants, a lot of floating points get shortened, all of these kind of things to make it smaller, to make it simpler to work on a mobile device. Then there's the interpreter that works on the mobile. So we currently are shipping TensorFlow Lite for Android and iOS, and we kind of shipped a preview, if you saw Google I/O, for Raspberry Pi, you know, for IoT type devices. So all that interpreter does is that's basically code that wraps that model. You pass data into it, it gives you data, you know, it gives you an answer back out. And then operation kernels and hardware acceleration delegates are things that are then optimized for particular devices. So I've mentioned a couple of mathematical functions, things like the ReLU and all that kind of stuff. When we talk about operations, that's what they are. So we ship it with a subset of the most commonly used operations, but every time you add a new operation, you increase the size of it, and we've been trying to keep it small. So not all operations supported by TensorFlow are supported in TensorFlow Lite, but we've shipped it so for some of the main scenarios we see in machine learning, like image classification, that kind of thing, it supports. And then depending on the device, like with various Android devices, there's hardware acceleration, there's GPU stuff, that kind of thing. So there are delegates for that. And like I mentioned, it's cross-platform, so if you're an Android developer, your Java, Kotlin, if you work in that, it will work with you. If you go down into the NDK with things like C++, it will work with that too. With iOS right now, it's only C++, so we haven't built like a Swift wrapper or an Objective-C wrapper on it. So if you're using TensorFlow Lite, you know, you'd have to either build your own wrapper or you go down into C++. And then we've been working with Linux, so for example, Raspberry Pi and other IoT things, and then you can go straight Python on that as if you were just running it on a Linux machine. And we get questioned a lot that a lot of people are iOS developers, they love CoreML. We love CoreML too. So we said, like, we've created a tool so that your trained TensorFlow model, instead of just converting to TensorFlow Lite format, can also be converted to CoreML format. And then you just use the CoreML as you would on an iOS device. So size-wise, we've been working really hard to shrink it. So right now, the core interpreter for TensorFlow Lite is only 75K on Android. And it's a little bigger on iOS, but not that much. I think it's like 80, 85. So 75K on Android. And that's with the core operations. If you add extra operations, like extra mathematical functions that you wanted to support, it can go up to about 400K, but it's still pretty small. So things like we've shrunk the interpreter, we've changed parsing, we've shrunk the model into something we call flat buffers. And you know, we've just been very, very careful and very tight with how we've developed it so that you have this really, really small runtime, put your model on that, and off you go. So let's give a demo of this, and I'm going to demo it. I'm going to attempt to demo it in an emulator, so bear with me for 1 second. If this doesn't behave, I have it running on my phone as well, and I can show it to you one-on-one. But I'm going to just drag this over. Oop. Doesn't work if the slide's running, right? Okay. Gonna run this over, and now you can see I'm emulating an Android device, and it's using the front camera from my laptop. But one of the things I want to do is, like, at the bottom here, you can see it thinks I'm a paintbrush, but you know, what it's doing is that it's taking frames from the camera and it's running those frames through a TF Lite model that's been trained on something called ImageNet. And ImageNet is trained to recognize, I think, about 5,000 images. So then for each frame that it captures from the camera, it passes that to ImageNet. And remember I spoke about one-hot encoding. It gets back an array of 5,000 items, and those 5,000 items are the probability that what it's looking at is that item. And then it picks the top 3 of those. So right now it thinks it's perfume. So it picks the top 3 of those, and then from those ones, then it just renders the top 3. Now, it doesn't work when there's a noisy background, but oops, my apple fell. But I'm going to try it with this. It thinks it's a conch. It's a banana, there we go. So now it actually sees, it's only a 10% probability that it's a banana. Like, it'll work a lot better against a plain background, but that will give you an idea. And then what I want to show is the number at the top. So that's like 493 milliseconds right now. That's the time that it was taking to do the inference. So it was taking a frame, and in about 500 milliseconds, it was then classifying 5,000 different things, picking the top 3 of those, and then rendering it in the UI. And that's in an emulator. You know, I'm going to run it on my actual phone. Oh, I've turned my phone off during the presentation. I'll run it a little bit later and show you. But it actually can do it like sometimes in about 10 to 20 milliseconds on real hardware. So pretty cool stuff. This is open source if you want to play with it. There's a number of pre-trained models based on famous image recognition algorithms that you can download. I'm using the one called ImageNet here. All right, how are we for time? 8, okay. So let me go back into presentation mode for a second. So next up then is, so, you know, first of all, it was talking about TensorFlow, talking about machine learning, how you can get started with machine learning. Then there was TensorFlow Lite. So with TensorFlow Lite, you will typically build your model on your development box, on your workstation with a GPU or something like that. The primary programming language for that is Python. And most examples and all that you'll see are in Python. How many people don't know Python? Okay, a few. I promise it is the easiest language in the world to learn. And I'll tell you a funny story about how I learned Python. And so how I learned Python, I joined Google 5 years ago. And I had this really weird thing that when I joined, that a week after I joined, my manager quit. And then the week after that, my mentor went on sick leave. And all of my team were in California, and I'm based in Seattle. And I was like sitting in an office by myself with nothing to do. I'm like, what do I do? And one person approached me and said, they have this project that they're working on, and it needs somebody with bandwidth. Can you help? And I'm like, I got nothing to do. I'll help. And the project was for a very famous boy band called One Direction. Anybody heard of them? I normally say One Direction, and somebody goes, ah! You know, I guess they're a bit passé now. But so, you know, and it was for One Direction, and they were launching a new album, and they were live streaming the launch of the new album on YouTube. And they wanted a second screen experience for this, and it was going to be and it ended up being the largest live streamed event in history on YouTube. It's since been superseded, but then it was that. And what they said is, like, we really want to show off how good Google Cloud is. And one of the selling points of something like Google Cloud is capacity isn't just big. It's a generally a misnomer that people think capacity means you can get really, really big. True capacity and true scalability means you can get really big when you need to, and you can scale right back down when you need to. And then you only pay for the capacity that you use. So they were like, this is the ideal opportunity to show that off, because One Direction are going to be doing this live stream, but what they want to do is every 10 minutes, the band are going to say, hey, everybody, go to this website and answer a question. And then when they answer the question, they're going to find the world's best One Direction fan, whoever, it was over the course of 7 hours with like a question every 10 minutes, who's going to get the most questions right, they'll become the #1 fan, that kind of stuff. But think about this from an architecture and programming perspective. You have a website that nobody visits, and then several million people watching a live stream of One Direction, and One Direction say, go visit this website now. Your traffic goes boom, people answer the question, your traffic collapses again. Right? So the idea was like to actually build out this application. So I honestly thought I was being hazed. Like they're saying, it was a joke, but it wasn't. And I ended up having to write this in Python. And that's how I learned Python. I ended up building that application, and it was a great success. And if you go onto YouTube, you'll find a video where I talk about how it was built and how it was architected, and it was like everything I learned about cloud scalability from working with boy bands. Anyway, so that's Python as your programming language. But one of the most popular programming languages that we constantly hear about is JavaScript. A lot of people don't like JavaScript, but they find it as a necessity. You got to write stuff that executes in the browser. And so we've been working really hard to produce TensorFlow.js, where the idea is with TensorFlow.js, you can run inference on models in the browser. So you can build your model somewhere else, like you do at mobile. You can deploy it to the browser, and you can run inference on that. Or if you prefer, you can actually train a model in the browser. So there may be scenarios where you're collecting data through the browser. And has anybody seen the Pac-Man demo? No? I'll see if I can run it in a moment. But we have a demo, if you go to js.tensorflow.org, that what it is the game of Pac-Man, and then you can train using your webcam of you looking up and you looking down and you looking left and you looking right. And then what that will do is then when you play Pac-Man, you move Pac-Man by looking around. It's kind of hard to do when you're not looking at the screen, but you get where I'm going, So that's like how you'd actually train stuff within the browser. So we've been working hard on TensorFlow.js, where the idea is that you can run it directly in the browser, or if you're a Node.js developer and you want to run JavaScript on the back end, you can do so too. So again, thinking about coding, how does coding work? All about machine learning. You feed in your answers, you feed in your data, you get your rules out. So when you're coding for ML, thinking of those terms that I was talking about earlier on, remember, it's all about your data. Start with your features, define what they are. Start with your labels, define what they are. You format the data with training in mind. The #1 place where you have to reformat your brain a little bit is to think about one-hot encoding. And then you design your neural network and train it. I want to show a little, and then constantly tweak your network, experiment with features, and then iterate. Do this while it's possible, while it's continually possible to do so. So let me give a quick demo of coding and what it would look like. We're a little short on time, so I'm going to just go through this one quickly. But here's an example. I'm in Genie in Linux. So here's an example that there is a data set. Whoops. There's a data set out there of iris data. The flower, the iris. So there's a public domain set of data for classifying iris flowers, where researchers measured 4 data points. It was like petal width and length and sepal width and length for irises. And then for 3 different types of iris, they classified them. So here, you remember earlier on I was talking about get the data in a format that your language can understand. So this is where I've gotten the data, and it was CSV data, but I've converted it into an array that JavaScript can understand. And you see there's a big JavaScript array here. Sorry if it's a little small if you're at the back. But the array, each array has 5 elements in it. The 4 measurements that I talked about earlier, and then a value 0, 1, or 2, where 0 is one type of iris, 1 is a different type, and 2 is a different type. So this is what the data came to me looking like in CSV. So what would you do with data like this? First thing you do is you convert it to using one-hot encoding, and I can release this source code. But it's a case of, it's just JavaScript. I've got an arrays. I can split them. I can split out that last column, and I'm going to make that my features, and then I can one-hot encode that. So where it was a 0, I'm going to replace that with 0, 0, 0. Where it was a 1, I'm going to replace that with 0, 1, 0. And where it was a 2, I'm going to replace that with 0, 0, 1, right? Those kind of things. Just getting my data, formatting my data, getting it ready for ingestion. And then I can train a neural network off of this. So if I go to tfs2.html, so just to give an example, sorry, this is really small and Genie doesn't let me make my fonts bigger, but this code here, there's maybe 12 lines of code there. That's all it takes to train a neural network. Okay, this is a very simple neural network. It's got one layer where it's processing the input features, and it's got one output layer with 3 neurons where it's going to give me, what type of flower it is. These lines here are defining those layers. I'm just compiling that, and then I'm training it. And I'll show you what it looks like when I train it in the browser. If If I can find my mouse. And okay, so it's here. So I have my developer tools turned on here. So I'm just going to refresh the page, actually. Oops, lost my mouse again. There we go. So over here, you'll see it's training. It's going to start training. There we go. This is training. So remember earlier I was saying you get data, try and figure out the values, take a look at your test set, see where it's wrong, optimize, change. So I've programmed it to go through 400 loops of this to see where I end up. So it's, this is training on, I can't remember, there's like 200 or 300 pieces of data with the iris. And it's about to go to loop 370, okay, it's at 400 now. So there, I've just trained something for 400 iterations. And this alert box that I'm doing is I just threw a piece of data at it that I knew would be for flower classification 2. And I'm printing out the 3 neurons. One said it was 0.00005% probability it was iris 0. The next one was 0.005 probability it was that iris. And then the next one was like a 99% probability it was that iris. So those are the values those 3 neurons are giving me. So I can tell pretty much easily, right, that it's going to be flower number 2, and that is correct. And then it just throws up a number 2 next, I believe. And again, yeah, it throws up a number 2. And the reason for this, and my prediction error rate here was 0. The reason for this, again, if I go back to my code, and there's something called argmax. So again, when you start looking at, when you start learning machine learning and start programming with that, there's all these mathematical functions. Now just don't be afraid of them. Just remember that their purpose is to prevent you writing a lot of if-thens. And the idea with this function called argmax is, if you imagine you got a big array of 5,000 values, and it's like lots of small values and one big one. If you pass that array into something called an argmax, what it will do is it will set everything to 0 and it will set the biggest one to 1. And that's all it does. Right? So it pulls the probabilities apart and it finds the one that you most want. So earlier you saw I had those 3 values for my 3 nodes. There were 2 very small ones and there was one that was 0.99. And instead of me writing an if-then to iterate through that to find the biggest one, it's easy if there's only 3. It's a bit harder if there are 5,000. You activate it, it's called activating. You activate it with something called, in this case, with the argmax function. And what the argmax function did is it sets everything to 0 except the biggest one. And as a result, I could tell the classification then from that without writing all of that code. So if you see my code here where I'm just saying prediction equals model.predict input, I gave it my input, it gave me back that array of values, I argmax that, it gives me the biggest one, and that's all it was. So that's a quick tour of machine learning, a quick tour of artificial intelligence, where we stand with it, with TensorFlow, why we're working on TensorFlow. Talk a little bit then also about the direction we're taking TensorFlow in mobile and TensorFlow for web with TensorFlow.js. So hopefully that was informative for you. I'm sorry I'm really horribly jet lagged, but thankfully I didn't fall asleep and nobody else did, even though I'm the only one allowed to. So just want to say thank you very much.
Thank you.
Thanks.